Hey everybody, Dr. A here, and in this video we're going to be exploring an example of allowable stress. So let's take a look at the given information. Here we're being given that a beam uses a bolted plate connection at point A in single shear. So that first sentence tells us that we have this plate that's got some bolts going through it that's experiencing single shear. The bolt shear strength is 350 megapascals and the diameter is 13 millimeters. Using a factor of safety of 3, what is the required number of bolts? So the first thing I want to point out is that just because the figure shows 2 bolts here does not mean that the answer is 2. That's just for illustrative purposes. We're actually trying to calculate the number of required bolts. So just because, again, the figure shows 2, it's really going to be a different number than that, and that's what we're going to figure out. So if we take a look at this beam, what we have here is a simply supported beam. This bolted plate connection is treated like an external pin connection, so like a little triangle shaped support here, external hinge, all right? And then we have a roller over at B. So this is a simply supported beam, and it's supporting a uniformly distributed load of 60 kilonewtons per meter, and the total length of the beam is 4 meters. So that's what we're looking at. So let's go ahead and tackle this. So the first thing we need to do is get that shear force that's passing through this bolted connection. Well, that shear force is really just AY, right? So I'm going to say V equals AY, and this is a simply supported beam with a uniformly distributed load over the entire span. So that's just going to be 60 kilonewtons per meter times 4 meters divided by 2, and that gives us 120 kilonewtons. Now, how do I know it's 60 times 4 over 2? Well, again, this is a simply supported beam, right? You have a pin and a roller, and it's subjected to a uniformly distributed load over the entire length, okay? So that means that the equivalent point load is the 60 kilonewtons per meter times 4 meters, and where is that located? Right in the middle of the load distribution, okay? And then that's going to get divided in half equally to AY and BY. All right, and so there's the divided by 2. Now, if you're wanting to exercise your knowledge of statics or you're not fully convinced of this, what you can do is apply an equilibrium equation just like you would have in a statics course, and you can say sum of the moments about point B, and you can solve for AY directly, and you should still get the 120 kilonewtons, okay? But this is just a faster way of performing this calculation when you have a symmetrically loaded, simply supported beam. It's just gonna transmit the total load into halves. Half of it goes to AY and half of it goes to BY, okay? So let's move on. What relationships do we have that we can use for a problem like this? Well, we know that factor of safety is equal to a failure scenario divided by an allowable scenario. So because we're dealing with shear stress, we're going to say tau fail over tau allow, okay? If it was bearing stress or some kind of normal stress, we would use sigma, but here we're using tau, okay? We also know that tau allow is equal to a shear force divided by a cross-section area of the bolt. Now, what is this shear force, this little v? Is it the exact same as this capital V that I wrote a few steps back? Not really, because we have multiple bolts. This little v right here, I'm going to rewrite that as that capital V divided by the number of bolts, and then that is still divided by the cross-section area. Okay, so this divided by N incorporates in the number of bolts that we could have in that connection. So we can rewrite this as V over N times A. All right, and so again, one more time, this little v right here represents capital V, which we calculated a couple steps above, divided by the number of bolts. All right, now we also know that what's the cross-section area of a bolt or of anything with a circular cross-section? That's going to be pi d squared over 4. And so what we can do here is take these relationships and combine them accordingly to solve for the thing we're looking for. And remember, we're looking for number of bolts in, all right? So how do we do this? Well, we could start substituting in numerical values. We could do that because we have pretty much all the numerical values we need. But I prefer us to do some algebraic manipulations first, because if we can solve a problem like this just using algebra before we substitute numerical values in, then we can solve any problem. It doesn't matter what the numbers actually are, all right? So let's go ahead and get started. So I'm going to take this factor of safety equation and I'm going to rearrange it. I'm going to say tau allow equals tau fail over a factor of safety. Now, what do we have here? We have two equations for tau allow. We've got tau allow is this relationship. We also have tau allow is tau fail over factor of safety. So we can set these two relationships equal to one another because they're both tau allow, okay? So I'm going to say V over N times A equals tau fail over Fs, okay? Now, what can I do next? Well, I know that my cross-section area is pi d squared over 4, so I can substitute that in for that area right there, all right? So then I'm going to say V over N times pi d squared over 4 equals tau fail over factor of safety. Now what am I left to do? Well, all I've got to do is solve for n right here, and I have all the other inputs that I need. So doing some algebra and rearranging, you should end up getting n equals 4v times the factor of safety divided by pi d squared times tau fail. So maybe pause the video and do your own algebra scratch work to go from this step to this step, okay? Do your own algebra to go from here to here so you can convince yourself of how we got to that point. Well, now we have all of these values, right? We've got capital V, we've got factor of safety, we've got the diameter, and we have tau fail all given to us. So I'm going to substitute all my values in. I'm going to say 4 times 120 kilonewtons times the factor of safety, which was given to us as 3, all divided by pi times, now what's that diameter? It was 13 millimeters, so that's 0.013 meters squared, and then tau fail was 350 megapascals, so we're going to need to convert that to 350,000 kilopascals. Why do we have to convert that? Well, it's because our shear force in the numerator is in terms of kilonewtons, and so you need consistent units. Now, what's an alternative for this? You could have converted the 120 kilonewtons to 0.12 meganewtons, and you could have kept tau fail just as 350 megapascals. But regardless, you need consistent units, so you need kilos in the top and the bottom, or megas in the top and the bottom, all right? So we're going to do some rearranging here, and we're going to get N equals, and we should get 7.75 bolts, okay? 7.75 bolts. Now, one comment here. Are you going to tell someone who is building this that they need 7.75 bolts? No. How in the world are you going to use 0.75 of a bolt? So we're going to say use N equals 8 bolts. Okay? We're going to say use N equals 8 bolts. Now, let's check our units. Okay? We're going to say unit check at the very end just to make sure that we get things that make sense. Okay? So notice in this numerator we have kilonewtons. So I'm going to say kilonewtons. And then denominator has meters squared. That's coming from the diameter squared right there. And then we also have kilopascals in the denominator. What's a kilopascal? It's a kilonewton per meter squared. Okay, so what happens here? Well, we should immediately see that the meters squared cancels and the kilonewtons cancel. And so you might be looking at this and saying, well, this is unitless. But it's not really unitless because we know what the meaning of V over N is. N is the number of bolts that is baked into our algebra. So we know even though the units come out as what seems to be nothing, we know that back up here when we set up this initial relationship, we said that this little shear force was kilonewtons per bolt, right? Kilonewtons per bolt. So N is a number of bolts. So that's why we come out with final units representing bolts, okay? So this is our final answer. We're going to say 8 bolts. And that will conclude this example. If you found this helpful, please hit like and subscribe and be on the lookout for other examples like this. Thanks for watching.